On the night of August 17, 1943, 596 Boeing B-17 Flying Fortresses took off from airfields across eastern England and flew into the darkness over occupied Europe on a mission that the 8th Air Force had been planning for 6 months and that its senior commanders had described in the classified briefings that preceded it as a mission that could shorten the war by a year. The target was Schweinfurt, Germany, the ball-bearing factories that supplied the precision components on which the entire German war machine depended, the tanks, the aircraft, the artillery, the submarines. Destroy Schweinfurt, and you strangled the Wehrmacht's ability to replace its mechanical losses. The logic was clean and compelling and had been validated by analysis that had consumed the attention of the best planners the Army Air Forces possessed. The logic did not account for the Luftwaffe's night fighters. Of the 596 aircraft that departed England that night, 60 were destroyed. 600 American airmen did not come home. Another 87 aircraft returned with damage so severe that they were removed from operational service. In human terms, the mission that was supposed to shorten the war had killed or captured more American airmen in a single night than some entire campaigns produced in a month. The mission is remembered in the history books as Black Thursday. In the barracks of the 8th Air Force's bomber groups across eastern England in the weeks that followed, it was not called anything. It was simply the thing that had happened, and that produced, in the men who had flown it and survived, and in the men who would be asked to fly similar missions in the weeks ahead, a quality of silence that those who observed it later struggled to describe in language that was accurate without being melodramatic. The silence was the recognition of a problem that the entire weight of American industrial air power had not solved. The problem was the night fighter. The German Bf-110 and the Ju-88 night fighter variants that the Luftwaffe had been developing and deploying since 1940, equipped with radar systems that could locate a bomber formation in complete darkness, guided by ground control networks that could vector them to within visual range of their targets, and armed with weapons that could destroy a B-17 from angles and distances at which the bomber's defensive gunners could not effectively respond. The problem had been studied by every level of 8th Air Force Command. It had been addressed by escort fighter development, by formation changes, by altitude adjustments, by radar jamming systems that were never quite good enough. It had consumed the planning capacity of intelligence sections and electronic warfare specialists and armament officers from one end of England to the other. The solution, when it arrived, came from none of them. It came from a staff sergeant named Albert Becker, who worked in the aircraft maintenance section of the 91st Bomb Group at Bassingbourn Airfield in Cambridgeshire, who had never attended a planning conference about the night fighter problem, who had never been consulted by an intelligence section about Luftwaffe radar capabilities, and who had been told when he first described his idea to his section chief that it was the stupidest thing he had heard in 14 months of this war. Becker wrote the idea down on a piece of paper and kept it in his breast pocket for 3 weeks while he thought about whether the section chief was right. Then he found a spool of copper wire and started working. Albert Becker was 29 years old in the autumn of 1943. He had grown up in Evanston, Illinois, the second son of a German-American family that had navigated the social complexity of that identity with the particular care of people who understood that their neighbors' memories were longer than the calendars suggested they should be. His father, Heinrich Becker, had anglicized his first name to Henry in 1917 and had never entirely unanglicized it. The family spoke German at home until 1918 and English exclusively thereafter. Albert grew up bilingual in a household that treated one of its languages as a private matter. He had studied electrical engineering for 2 years at Northwestern University before money ran out in 1933, in the specific way that money ran out for families of modest means in 1933, which is to say all at once and without adequate warning. He had taken work as an electrician's apprentice, then as a journeyman electrician working commercial and industrial installations across the Chicago area. He understood electricity not as an academic subject, but as a material phenomenon, something with physical behavior that could be observed and measured and manipulated, that followed rules that were consistent enough to be relied upon and complex enough to produce surprises if you stopped paying attention. He had developed in 12 years of electrical work a habit that his colleagues found unusual and his supervisors found useful. He listened to the systems he worked on. Not literally, or not only literally, though there was a component of literal listening, the ability to diagnose a failing component by the sound it made under load, that was part of the electrician's practical toolkit. He listened in the broader sense that he maintained an ongoing attention to the behavior of electrical systems that was not limited to the specific task he was currently performing. When he was wiring a building, he was also noticing how the building's existing electrical environment interacted with what he was adding to it. When he was troubleshooting a fault, he was noticing what the fault's behavior told him about the system's overall state, not just the immediate problem. He had been drafted in 1942 and assigned to aircraft maintenance on the basis of his electrical background, which the Army's classification system identified as relevant to the increasingly complex electrical systems that modern aircraft carried. He was correct in this assessment. A B-17 Flying Fortress carried more electrical wiring than a large commercial building of the era. Its systems, the gun turret motors, the bomb release mechanisms, the interphone communications, the navigation instruments, the heating systems that kept crews alive at 25,000 feet where the temperature was 50 degrees below zero, all required the kind of systematic understanding that Becker had spent 12 years developing in civilian work. He was good at his job. His section chief, a technical sergeant named Morrison from Georgia, who had been maintaining aircraft since 1938, said that Becker could find an electrical fault in a B-17 faster than any man he had ever supervised, not because Becker was faster in his physical movements, but because he seemed to understand what the fault was before he had finished looking for it, as if the aircraft's electrical behavior announced its own problems to him in a language that he alone could reliably read. Morrison did not say this with admiration. He said it with the specific discomfort of a supervisor whose subordinate is better at the core task than he is, which produces in some supervisors the desire to find other areas in which the subordinate's limitations can be more firmly established. When Becker described his wire idea for the first time in October of 1943, Morrison found his area. He told Becker it was the stupidest thing he had heard in 14 months. Becker wrote it down and kept it in his pocket and went back to work. To understand what Becker was attempting to solve, you have to understand the mechanism by which German night fighters found and destroyed American bombers in the dark over occupied Europe, because the mechanism was not simple. It was not a matter of German pilots with exceptional eyesight scanning the dark sky for silhouettes. It was a system, layered, coordinated, technically sophisticated, that the Luftwaffe had spent 3 years developing and refining in response to the RAF's night bombing campaign, and which by 1943 had become the most lethal component of Germany's air defense network. The foundation of the system was radar. The Germans had developed several radar systems for air defense purposes, the most significant of which, for the night fighter mission, was the Liechtenstein airborne intercept radar carried by the Bf-110G and Ju U-88C night fighter variants. The Liechtenstein operated at a frequency of approximately 490 MHz. Its antenna array, mounted on the aircraft's nose in a configuration that the RAF and American intelligence services described as resembling a metal bed spring, and that reduced the aircraft's maximum speed by roughly 25 miles per hour, could detect a large aircraft like the B-17 at ranges up to 4 kilometers. 4 kilometers in darkness was the difference between finding the target and flying past it forever. The system worked in layers. The outermost layer was the ground radar network, the Freya and Würzburg radar installations that covered Germany's borders and could detect incoming bomber formations at distances of 150 kilometers and beyond. This network fed information to the ground control centers, which translated the radar data into vectors, headings, and altitudes that were transmitted by radio to the night fighter crews. The night fighter pilot would fly the vector given by his ground controller, closing on the bomber formation from a direction and altitude calculated to place him within range of his own airborne radar. When the Liechtenstein picked up a contact, the night fighter pilot handed control of the approach to his radar operator, who guided the pilot toward the target using the radar's azimuth and elevation displays. The approach was typically made from behind and below, where the bomber's defensive armament had the poorest coverage. The Bf-110G standard armament included two 30mm cannon firing upward from a fixed installation behind the cockpit, a system the Germans called Schräge Musik, oblique music. The night fighter would slide into position below the bomber, pull the nose up slightly, and fire upward into the bomber's fuel tanks and bomb bay. The bomber crew often never saw the night fighter. The first indication of attack was frequently the explosion. The Liechtenstein radar was the link that made this possible. Without it, the ground vectors could bring the night fighter into the right area of sky, but could not solve the final approach problem in darkness. With it, the radar operator could guide the pilot to within 100 meters of the bomber before visual acquisition became possible. And at 100 meters in darkness, a B-17 was visible enough to aim at. The American response to the Liechtenstein had been electronic. The RAF had developed the Monica tail warning radar and the Serrate homer, which could detect Liechtenstein emissions and allow a fighter to home on the night fighter. The Americans had developed various jamming systems designed to saturate the Liechtenstein frequency with noise that prevented the radar from resolving a clear return. These systems worked partially. They degraded the Liechtenstein's performance. They did not defeat it. Becker knew about the Liechtenstein from the intelligence briefings that circulated through his group, and from conversations with returning crews, and from his own reading of whatever technical material about German radar systems the 8th Air Force's intelligence sections made available to maintenance personnel, which was less than Becker wanted and more than most of his colleagues read. He knew that the Liechtenstein worked by sending out radio waves and detecting the energy that bounced back from the target. He knew that the strength of the return signal depended on the size of the target and the reflective properties of its surface. He knew that the jamming systems the Americans were using addressed the signal that the radar sent out, trying to overwhelm it with noise, rather than the signal that came back from the aircraft. He had been thinking for 3 weeks with the paper in his breast pocket about the signal that came back from the aircraft. He was thinking about what happened if you changed the aircraft instead of the radar. Radar works by transmitting radio energy in a directed beam, waiting for that energy to bounce off a target and return to the receiver, and measuring the strength and timing of the return to determine the target's range, direction, and speed. The energy that returns to the receiver, the radar cross-section in the language of the engineers who designed these systems, depends on 2 things: the physical size of the target and the way the target's surface reflects the radio energy. A large flat surface perpendicular to the radar beam reflects energy back toward the source with high efficiency. A large curved surface reflects energy in many directions, scattering it so that only a fraction returns to the receiver. A surface covered with material that absorbs radio energy rather than reflecting it returns almost nothing at all. In 1943, radar-absorbing material did not exist in practical deployable form. The theoretical understanding of how it might work existed. The material science required to produce it did not. The German engineers who built the Liechtenstein and the American engineers who built the jamming systems against it were both operating in a technological environment in which the radar cross-section of an aircraft was essentially determined by the aircraft's shape and could not be practically altered by coating it with absorbing materials. What could be altered was the way the aircraft's metal surfaces reflected radio energy, not the absorption, the scattering. A surface that scattered the incoming energy in many directions rather than returning it coherently to the source would reduce the effective radar cross-section without absorbing any energy at all. The aircraft would still reflect radar energy. It would simply reflect it in directions that did not include the direction of the radar receiver. This is the physics of what Becker had been thinking about for 3 weeks. He was not a radar engineer. He had 2 years of electrical engineering coursework from 1931 and 1932, and 12 years of practical electrical work. His understanding of radio wave behavior was the understanding of a man who had worked with radio frequency systems in industrial installations, power conditioning, interference suppression, the management of electromagnetic fields in environments where precision electrical equipment needed to function without disruption from nearby machinery. In that work, he had learned something about how radio frequency energy behaved around metal structures. He had learned that thin wire, strung in specific geometric patterns, could create interference patterns in radio frequency fields, could redirect, cancel, or scatter radio energy in ways that the bulk metal structures around it could not. He had used this knowledge to solve industrial interference problems. He had strung wire grids inside electrical panels to redirect high-frequency noise away from sensitive components. He had created what the textbooks called parasitic elements, wire structures that did not carry current, but that interacted with electromagnetic fields to change the way those fields propagated. He had been sitting in the maintenance hangar one evening in late September, reading a technical intelligence summary of the Liechtenstein radar's operating characteristics, frequency, antenna configuration, pulse repetition rate, and he had thought, with the specific quality of recognition that comes from connecting two things that have been separate in the mind for a long time, parasitic elements. The Liechtenstein operated at 490 megahertz. At 490 megahertz, a quarter wavelength dipole element, a piece of wire cut to a specific length, would resonate. It would interact with the radar's electromagnetic field in a predictable way, scattering the incoming energy rather than allowing it to reflect coherently from the bomber's metal surfaces. An array of such elements positioned along the bomber's fuselage at calculated intervals would create a scattering pattern that reduced the coherent return to the Liechtenstein's receiver without absorbing any energy, without requiring any electronic system to the aircraft. It was wire, copper wire cut to specific lengths and strung along the fuselage in a grid pattern. It was so simple that Morrison had called it stupid. Becker thought it might be so simple that it worked. The 3 weeks between Morrison's dismissal and Becker's decision to proceed were not 3 weeks of inactivity. They were 3 weeks of the most careful private thinking that Becker had ever done about a technical problem, conducted entirely in his head during the working hours of a maintenance schedule that left him 12 hours of each day in direct physical contact with B-17s. He worked on the aircraft every day. He traced wiring faults, replaced failed components, tested circuits, calibrated instruments. He did all of this with the divided attention of a man whose hands were solving one problem while his mind was working on another. The mind's problem was the wire grid. The hands' problem was whatever the maintenance schedule required. Both problems received full competence. The wire grid received, additionally, every spare moment of the mind's capacity throughout those 3 weeks. He was working through the engineering in the only way available to a man who had left university 20 years before and who did not have access to the university's laboratories and equipment, by calculation, by reference to the physical intuition built from 12 years of practical electrical work, and by the specific test of internal consistency that a technical idea either passes or fails when you examine it closely enough for long enough. The calculations were not elegant. They were done in the margins of the maintenance logs and on the backs of requisition forms, and occasionally on the palm of his hand when no paper was available. They were the calculations of a man who understood the principles well enough to know what he needed to calculate, but who was working without the precision instruments that would have made the calculation definitive. He was estimating, he was bounding, he was determining, as precisely as his available tools allowed, whether the idea was physically plausible or whether Morrison had been right. By the end of the second week, he had determined that the physics were sound. The quarter wavelength dipole for 490 megahertz was 15.3 centimeters, 6 inches of copper wire. An array of such elements spaced at half-wavelength intervals along the fuselage, 30.6 centimeters apart, would create a resonant structure that interacted destructively with the coherent radar return from the fuselage's metal skin. The destructive interaction would not eliminate the radar return entirely. Becker did not claim, even to himself, that it would make the aircraft invisible, but it would reduce the coherent return, the portion of the reflected energy that traveled back toward the Liechtenstein's receiver in a direction and phase that the receiver could resolve into a clear contact, by a factor that his calculations suggested was significant. How significant was the number he could not calculate without testing? The calculation required knowledge of the exact radar cross-section of a B-17 at the Liechtenstein's frequency and the exact scattering characteristics of the wire array's resonant structure, both of which required measurement rather than calculation to determine with the precision needed for a reliable answer. The third week was the week he thought about Morrison. Morrison was not a stupid man. He was experienced and practical and had spent 5 years maintaining aircraft that the Army trusted him to keep functional. His dismissal of the wire idea had not been casual. He had looked at Becker's description of the concept with the attention of a man who takes his work seriously, and he had said it was stupid, and he had said it with the confidence of a man who believes he is right. Becker spent the third week trying to find the error in his own thinking that Morrison's confidence implied. He looked for the flaw in the physics. He looked for the assumption he had made without examining it. He looked for the point at which the practical implementation would fail in a way that the theoretical analysis had not revealed. He found 3 concerns. The wire array would add aerodynamic drag, small but possibly significant at high altitude where engine performance was marginal. The array would need to be attached to the fuselage in a way that survived the vibration and thermal cycling of combat operations without coming loose and creating a foreign object hazard to the aircraft's control surfaces. And the array's effectiveness would depend on the Liechtenstein's exact operating frequency, which was known from intelligence, but which might vary between individual installations and might have been changed by the Germans since the most recent intelligence assessment. 3 concerns, none of them fatal, all of them addressable through careful design and testing. He pulled the paper out of his breast pocket on the morning of the 18th day. He read it again. He put it back. On the 19th day, he went to the supply room and signed out a spool of 18-gauge copper wire on a maintenance requisition that described its intended use as general electrical repair work, which was accurate enough to be defensible. He took it to his workbench and began cutting 6-inch lengths. The B-17 that Becker chose for his first installation was a G model assigned to the 91st Bomb Group's 323rd Bomb Squadron, aircraft serial number 4231592, named by its crew Hell's Librarian, in reference to a running joke about its bombardier who read obsessively between missions and who had been seen, on at least 2 occasions, reading in the aircraft while waiting for engine start. The crew called the aircraft the Library. The maintenance section called it 592. Becker called it his test article, privately, in the privacy of his own mind, where the project still had no official existence and therefore required no official designation. He chose 592 because it was scheduled for 3 days of maintenance downtime following a hydraulic system repair that had required the removal and replacement of the landing gear actuators on both main mounts. The 3 days of downtime gave him access to the aircraft without the presence of the crew, without the pressure of a departure schedule, and with enough unobserved time to install the wire array carefully enough that it would survive flight operations without failing. He worked on the installation for 2 evenings after his regular shift, between 1800 and 2200 hours, in the section of the maintenance hangar where 592 was parked, with its maintenance panels open and its systems partially disassembled. He told the hangar duty sergeant that he was completing additional electrical system checks related to the hydraulic repair. This was not entirely false. The hydraulic system's electrical controls had been disturbed during the repair and did require verification. The wire array installation required 4 hours of careful work. He had cut 180 6-inch lengths of copper wire in his quarters the previous evening, measuring each one against a template he had made from a piece of cardboard marked at exactly 153 millimeters. The precision of the length was important. The resonant frequency of a dipole element is inversely proportional to its length. A wire 6% too long resonates at a frequency 6% too low. At 490 MHz, a 6% error represented 29 MHz of detuning, which would significantly reduce the array's effectiveness at the Liechtenstein's operating frequency. He attached the wire elements to the fuselage using small adhesive clips that he had fabricated from strips of aircraft aluminum tape, the same tape used throughout the maintenance section for sealing access panels and patching small surface damage. The clips held each wire element perpendicular to the fuselage's longitudinal axis, which was the orientation that produced the maximum resonant interaction with a radar signal arriving from the front or rear of the aircraft, the directions from which the night fighter made its approach. He spaced the elements at 306 millimeters, the half-wavelength spacing that his calculations indicated would produce the strongest destructive interference with the coherent radar return. He ran 5 rows of elements along each side of the fuselage, from the nose section back to the waist gun positions, covering the maximum fuselage length that the access considerations allowed. The total installation used 180 wire elements and covered approximately 11 meters of fuselage length. When he finished the installation and stepped back to look at it, the effect was striking in a way he had not anticipated. The B-17's aluminum fuselage, which normally presented a smooth, clean surface that reflected the hangar's overhead lights in broad, even highlights, was now covered along its sides with a fine grid of short copper wires that caught the light and scattered it in 1,000 small reflections. The aircraft looked from certain angles as if it had been decorated, as if someone had applied a pattern to it for reasons that a maintenance sergeant would find very difficult to explain to his section chief if the section chief happened to walk through the hangar in the next 90 minutes. No one walked through the hangar. Becker covered the wire array with removable panels that would be replaced during the next day's maintenance work and would hold the installation in place and out of sight until 592 flew its next mission. He was not yet finished. The installation was the physical component. What he needed now was the test. He could not test the wire array against an actual Liechtenstein. He did not have access to one. What he had was the maintenance section's radar test equipment, instruments designed to check the B-17's own radar systems, and his own understanding of how radar return measurement worked. He set up the test at the far end of the maintenance apron in a clear night in early November, using the section's signal generator to produce a test signal at 490 MHz aimed at 592's fuselage from a distance of 50 meters. He measured the return strength with a calibrated receiver borrowed from the electronics maintenance section on a pretext he later described, when asked, as creative. He measured the return from the nose section of 592. He measured the return from the wire array-covered fuselage section. The wire array reduced the coherent return at 490 MHz by approximately 40%. Becker sat with this number for a long time in the cold November dark on the maintenance apron. 40% was not invisibility. 40% was significant. A 40% reduction in radar return strength meant that the Liechtenstein would detect 592 at a range 23% shorter than it would detect an unmodified B-17, not 4 kilometers, 3 kilometers and 90 meters. In a night fighter intercept, 900 meters of detection range was the difference between a radar operator who had time to guide his pilot through a careful approach and a radar operator who was still refining his contact when the bomber flew out of range. It was the difference between a methodical attack from below and a rushed approach that disrupted the Schrage music firing geometry. It was, in the specific mathematics of survival probability, that every bomber crew calculated privately and continuously throughout their tour, a number that mattered. He took his measurements back to his quarters and wrote them up in the same notebook where he had been keeping his calculations for the past 3 weeks. He read what he had written 3 times. Then he went to find someone who had the authority to do something with what he had found. Becker's first approach was to Morrison, because Morrison was his direct supervisor, and going around him would create a personnel problem that would follow the wire array project into whatever future it had. He asked for 15 minutes. Morrison, who had not forgotten their previous conversation about the wire idea, gave him 10, and spent the first 2 looking at Becker with the expression of a man who had already decided the direction of his response. Becker put the notebook on Morrison's desk and pointed to the measurement data from the apron test. He explained the numbers. He explained what a 40% reduction in radar return meant in terms of detection range. He explained the physics of the quarter-wavelength dipole array in language that he had spent 3 days translating from its original electrical engineering vocabulary into the vocabulary of a man who understood aircraft systems but had not studied antenna theory. Morrison listened for the remaining 8 minutes. He looked at the data. He looked at Becker. He looked at the data again. He said that Becker's methodology was not rigorous enough to support the claimed result. He said that a signal generator and a borrowed receiver on a maintenance apron at 50 meters did not replicate the conditions of a Liechtenstein radar tracking a B-17 at 4 kilometers in flight. He said that the installation on 592 was unauthorized and needed to be removed before the aircraft flew its next mission. He said that if Becker wanted to pursue the idea, he should write it up formally and submit it to the group's technical officer for evaluation. This was not a dismissal. It was, from Morrison, a significant concession, an acknowledgement that the idea warranted formal consideration rather than immediate rejection. Becker recognized it as such and accepted it as such, and thanked Morrison and went to write the formal submission. The group's technical officer was a first lieutenant named Calloway from Boston, who had studied physics at MIT before the war, and who read Becker's submission in one sitting, and then read it again, and then called Becker to his office and asked him to explain the antenna theory behind the quarter-wavelength dipole array from first principles. Becker explained it. Calloway listened with the focused attention of a man who knows enough about a subject to assess whether the person explaining it also knows enough about it. He asked 4 technical questions. Becker answered 3 of them correctly and answered the 4th approximately correctly, acknowledging the approximation and explaining why the approximation was sufficient for the application. Callaway said that the physics were sound, but that the methodology was inadequate, and that the installation on 592 needed proper evaluation before the aircraft flew with it. He said he would arrange for a proper measurement using the group's radar calibration equipment and a controlled test setup. He said this would take a week to organize and that 592 should be grounded until the evaluation was complete. He also said, and he said this in the specific tone of a physicist who had been working in an operational environment for 14 months and has learned that the gap between theoretical soundness and operational approval is wider than the textbooks suggest, that even if the evaluation confirmed Becker's numbers, getting the modification authorized for operational use would require documentation, testing, and review that could take months. Becker said he understood. Callaway looked at him for a moment. Then he said that in the meantime, he was going to write a memo to 8th Air Force Headquarters describing the concept and the preliminary results and requesting priority evaluation, because if the numbers held up, the modification had implications beyond the 91st Bomb Group that could not wait for the standard approval timeline. He wrote the memo that afternoon. The memo reached 8th Air Force Headquarters at High Wycombe on November 14, 1943. It was read by a signals intelligence officer named Major Pratt, who had been working on Luftwaffe radar counters for 7 months, and who called Callaway within 2 hours of reading it and asked when he could visit Bassingbourn. Pratt visited on November 17th. He brought with him a physicist from the RAF's telecommunications research establishment at Malvern, who had been working on radar cross-section reduction for 2 years, and who, upon examining Becker's wire array installation on 592 and reviewing his calculations and test data, said something that Becker would remember for the rest of his life. He said that the approach was correct, that the specific implementation had limitations that he could identify, and that he could suggest improvements that would increase the array's effectiveness significantly, but that the fundamental insight, the use of resonant wire elements to scatter rather than absorb radar energy at the operating frequency of the specific radar system being countered, was not only correct, but was more practically implementable than any approach he had seen proposed by his own team or the American electronic warfare specialists. He said that a maintenance sergeant from Evanston, Illinois, had arrived at a solution that the telecommunications research establishment had been working toward for 2 years and had not yet reached. He said this with the specific generosity of a scientist who is more interested in the truth than in the credit. The RAF physicist's name was Dr. Harold Sefton. He was 41 years old, a Cambridge-trained physicist who had spent the years before the war studying electromagnetic scattering problems in the context of atmospheric optics, how light scattered from water droplets, how radio waves propagated through the ionosphere. He had been recruited into the telecommunications research establishment in 1940 and had spent the subsequent 3 years applying his understanding of electromagnetic scattering to the problem of making British aircraft harder for German radar to detect. His team at Malvern had been working on radar-absorbing coatings, materials that would absorb radar energy rather than reflecting it. The theoretical basis for such materials was well understood. The material science was the problem. The substances that most effectively absorbed radio frequency energy at centimetric wavelengths were heavy, difficult to apply uniformly, degraded in the operational environment of a combat aircraft, and were not available in quantities sufficient to coat an entire bomber fleet, even if the application problems had been solved. Becker's wire array addressed none of the problems that Sefton's team had been working on, and solved none of the problems they had failed to solve. But it solved a different version of the same problem through a mechanism that Sefton's team had not pursued. and it solved it with materials that were available in any maintenance hangar in England in quantities sufficient to equip every B-17 in the 8th Air Force. Sefton spent 2 days at Bassingbourn. He measured, he calculated, he tested. He identified 4 specific improvements to Becker's original installation that would increase the array's effectiveness at the Liechtenstein's operating frequency, while reducing its aerodynamic impact and improving the installation's durability under operational conditions. The first improvement was element orientation. Becker had mounted all elements perpendicular to the fuselage axis, which maximized their interaction with radar signals from ahead and behind, but reduced their effectiveness against signals arriving from the beam, from the side. Sefton showed that alternating the element orientation between perpendicular and diagonal created a broader scattering pattern that maintained effectiveness across a wider range of radar approach angles. The second improvement was element grouping. Rather than distributing individual elements uniformly along the fuselage, Sefton showed that grouping elements in clusters at specific intervals created resonant interactions between the clusters that amplified the scattering effect, producing a larger reduction in coherent radar return than the same number of individually distributed elements. The third improvement was element length variation. A pure quarter-wavelength array was tuned to a single frequency. By varying the element lengths across the array, mixing quarter-wave, 3/8 wave, and 5/8 wave elements in a calculated pattern, the array's effective scattering range could be broadened to cover a frequency band rather than a single frequency. This addressed Becker's third concern, the possibility that the Liechtenstein's operating frequency had shifted, by making the array effective across a range that encompassed plausible frequency variations. The fourth improvement was installation method. Becker's aluminum tape clips were functional but added frontal area and created small aerodynamic disturbances. Sefton showed that the elements could be attached more cleanly using the aircraft's existing external antenna attachment points and a modified clip design that added less than 1% additional frontal area. With Sefton's improvements incorporated, the array's reduction of coherent radar return at the Liechtenstein's operating frequency increased from Becker's measured 40% to approximately 68%. A 68% reduction in radar return reduced the Liechtenstein's detection range from 4 kilometers to approximately 2.4 kilometers. From 4 kilometers to 2.4 kilometers, a reduction of 1.6 kilometers in the night fighter's detection range. In the mathematics of a night fighter intercept, 1.6 kilometers was not a marginal improvement. It was the difference between a night fighter crew that had time to make a methodical, unhurried approach from the optimal attack angle, and a night fighter crew that was reacting to a late contact and rushing an approach from whatever angle was available. Rushed approaches meant disrupted shrug-a-music geometry. Disrupted geometry meant shots taken at non-optimal angles. Shots at non-optimal angles missed more often than shots from optimal angles. This was arithmetic, not hope. Sefton and Becker spent the last evening of Sefton's visit at Bassingbourn making their joint measurements and comparing notes. They were, by temperament and training and age and nationality and every other dimension of comparison available, entirely different kinds of men. Sefton was formal, precise, unhurried in the manner of a Cambridge don who had learned that the pace of thought should not be accelerated to meet a deadline. Becker was direct, practical, accustomed to working within the constraints of what was available rather than what was ideal. They got along immediately and completely. Sefton told Becker on the last evening that the wire array was the most practically elegant solution he had encountered to the radar cross-section problem. Not the most theoretically sophisticated, the most practically elegant. The distinction, he said, was important. Theoretical sophistication was something laboratories produced. practical elegance was something operational environments demanded. Becker had produced what the operational environment demanded because he had been inside the operational environment. Sefton said this was a lesson that his own institution had not fully learned. He said it with the self-awareness of a scientist who has spent enough time in the real world to know where the gap is between what he does and what needs to be done. The modified wire array, incorporating Sefton's 4 improvements and built to the joint specification that he and Becker had developed over the 2 days of testing, was installed on Hell's Librarian, B-17G serial 4231592 on November 22, 1943. The installation took 6 hours, 3 more than Becker's original installation had required, because the improved clip design and the varied element orientations required more precise positioning than the original uniform grid. Becker did most of the physical installation himself. Sefton supervised the positioning of the grouped element clusters, verifying the spacing with a measuring tape and a level of precision that Becker initially thought excessive and then recognized as correct when Sefton explained the sensitivity of the resonant interaction to positioning errors greater than 5% of the element spacing. The crew of Hell's Librarian was briefed on the modification by Callaway the morning of the installation. The briefing was conducted in the group's operations room, with Becker present. Callaway described the physics in terms accessible to men who were not physicists, but who had a practical understanding of radio systems from their experience with the aircraft's communications and navigation equipment. The pilot, a captain named Drummond from Denver, asked 2 questions. The bombardier, who read between missions, asked 6. The navigator said nothing but took notes. Drummond's questions were practical. Would the wire array affect the aircraft's radio systems? Becker said he had checked for interference during the ground test and found none at the frequencies used by the aircraft's communications and navigation systems. Would the array affect the aircraft's performance? Becker said the additional drag was estimated at less than 2 miles per hour at cruise speed, which was within the normal variation between individual aircraft of the same type. Drummond nodded. He looked at the notes he had made during the briefing. Then he asked the question that all the other questions had been leading to, the question that was not technical, but that mattered more than the technical questions. He asked if it would keep his crew alive. Becker said he did not know. He said that the physics were sound and the measurements were consistent, and the reduction in radar return was real. He said he could not promise that the reduction would be enough because he did not know enough about the variability of night fighter intercept geometry to translate a detection range reduction into a survival probability improvement with the precision the question deserved. He said that the modification gave the crew a better chance than they had without it. He said that was all he could honestly claim. Drummond said that was an honest answer and that he would fly with the installation. Hell's Librarian flew its first mission with the wire array on November 24, 1943, a daylight mission to Bremen. The Liechtenstein operated at night, but the mission established that the installation survived flight operations without coming loose, without creating control surface problems, and without affecting any of the aircraft's systems in a way that the crew noticed. Its second mission was a night operation on November 28th, a raid on Frankfurt as part of a coordinated 8th Air Force and RAF Bomber Command effort against the city's industrial infrastructure. The 91st Bomb Group provided 12 aircraft for the mission. Hell's Librarian was one of them. 11 of the 12 aircraft returned to Bassingbourn. Hell's Librarian was one of the 11. The after-action report recorded no contact with night fighters for 592 during the mission. The crew reported that they had observed night fighter activity in the vicinity of the formation, aircraft visible through the cockpit glass, the flash of Schräge fire from below, the sudden disappearance of aircraft in the formation around them. They had not been attacked. This was one data point, one mission, one aircraft, no attack. It proved nothing by itself, Night fighter attacks were not uniformly distributed across every aircraft, in every formation, on every mission. An aircraft could fly through 10 night fighter engagement zones and not be attacked by chance rather than by design. But the crew of Hell's Librarian flew it again on December 1st, and again on December 8th, and 4 more times before the end of December. 6 night missions in 5 weeks. The wire array remained in place through all of them, inspected before each mission by Becker, retensioned where vibration had loosened individual elements, and confirmed functional by the signal generator test that Becker conducted on the maintenance apron after each mission. Hell's Librarian was not attacked by a night fighter in any of those 6 missions. The statistics were not yet conclusive, they were suggestive, and suggestion in the operational environment of a bomber group that had been losing aircraft at rates that translated directly into the faces of men in morning briefings who had been at the previous morning's briefing and were not at this one, was something that the group commander could not ignore. He called Calloway in on December 15th and asked what it would take to install the wire array on every B-17 in the group. The 91st Bomb Group operated between 35 and 48 aircraft at any given time in late 1943, depending on losses and replacements. Installing the wire array on every aircraft in the group required a standardized installation process, a reliable supply of the specific materials the installation needed, and a quality control system that ensured each installation met the positioning specifications that Sefton had established as critical to the array's effectiveness. Calloway had all of this organized by December 20th. The installation process was documented in a 6-page procedure that Becker and Calloway wrote together over 3 evenings, precise enough to be followed by any qualified maintenance technician, clear enough to be understood without the theoretical background that Becker and Sefton had used to develop the underlying specifications. The material requirements were simple: 18-gauge copper wire, the modified clip design that Becker had fabricated tools to produce at scale, and a measuring template cut from sheet aluminum that positioned each element correctly without requiring the installer to calculate spacing independently. The installation time per aircraft was 8 hours using a 2-person team. For 40 aircraft, with 4 installation teams working simultaneously, the full group installation would take 5 days. Calloway proposed beginning on December 22nd, using aircraft downtime during the Christmas maintenance stand-down period. The group commander approved. Becker ran the installation program. He trained the 8 technicians who would form the 4 installation teams in 2 days of intensive instruction, covering the physics sufficiently for the technicians to understand why the positioning precision mattered, and covering the installation procedure in sufficient detail that they could execute it without supervision once Becker had verified their first installation. By December 27, 1943, the 91st Bomb Group was the first American bomb group in England to have every operational B-17 equipped with a resonant wire array designed to reduce its radar cross-section at the Liechtenstein's operating frequency. News of the installation program had traveled up the chain faster than Calloway's memo had originally suggested it would. The 8th Air Force's Electronic Warfare Section, which had received Calloway's original memo and had assigned it a medium priority review status, reassigned it to urgent after a second memo from Calloway describing the Hell's Librarian mission record and the group-wide installation program. Major Pratt drove to Bassingbourn on December 29th and spent the day with Becker reviewing the installation program, the quality control records, and the mission data that Calloway had been compiling since November. Pratt was a careful officer. He did not make statements he could not support. He looked at the mission data, 6 night missions, no attacks, against a group average of 1 attack per 4 night missions in the preceding 3 months, and he said that the sample size was too small for statistical confidence, but too consistent to ignore. He asked Becker if the installation could be standardized for production, fabricated to a specification that a supply depot could manufacture rather than a maintenance section on site. Becker said yes. He said the clip design needed 2 small modifications to be machine fabricated at scale, and the wire elements needed a cutting jig that could be operated by unskilled labor at a depot rather than requiring a trained technician on site. He said he could specify both modifications in writing within a week. Pratt said to do it. The specification was submitted to 8th Air Force Headquarters on January 7, 1944. It was forwarded to the Army Air Force's Material Command on January 9th. The Material Command's engineering review, which in normal circumstances took between 3 and 6 months, was completed in 11 days because Pratt had accompanied the specification with a cover letter that described the Hell's Librarian mission record and stated plainly that the modification appeared to be reducing night fighter attack rates in the one group that had deployed it, and that the standard timeline was not compatible with the rate at which bomber crews were dying while the review was conducted. The Material Command approved the specification on January 20, 1944. Production kits, pre-cut wire elements, fabricated clips, installation templates, and procedure documents were delivered to the first 10 B-17 groups in England by February 15th. Full 8th Air Force coverage was achieved by March 10, 1944. Over 900 B-17s received the wire array. The modification was given a technical designation, AN/APQ-9 Radar Scatter Array, which appeared in no press release and no public communication, and which the Army Air Forces described, when asked about it, by the few journalists who became aware of its existence, as an experimental electronic countermeasures system. The description was technically accurate and operationally uninformative, which was the intended effect. Becker was promoted to technical sergeant on February 1, 1944. The promotion order cited outstanding technical performance in aircraft systems maintenance. It did not mention the wire array. The modification's existence was classified. Morrison, who had called the idea stupid 4 months earlier, signed the paperwork. He did not comment on this in any document. He signed it in the specific silence of a man who understands that some moments are best navigated without speech. Measuring the operational effectiveness of the wire array was not straightforward. Bomber losses had many causes: flak, fighter attack, mechanical failure, weather, navigation error. Separating the effect of the wire array from the effect of every other variable that influenced night fighter attack rates required the kind of controlled analysis that operational environments rarely permitted. The 8th Air Force's Statistical Analysis section attempted this separation using before and after comparisons within groups and between groups over the period from December 1943 to April 1944. The analysis controlled, imperfectly, for mission difficulty, escort fighter availability, weather conditions, and the natural variation in loss rates that accompanied changes in German defensive posture over time. The result was not a clean number, it was a range. The analysis found that night fighter attack rates against B-17s equipped with the wire array were between 22 and 41% lower than attack rates against unequipped aircraft flying similar missions during the same period. The range reflected the uncertainty in the analysis's control variables. The lower bound was conservative. If everything else that had changed during the period had been fully accounted for, the array's effect might be as small as 22%. The upper bound reflected a less conservative control approach. 22 to 41%. Against a night fighter attack rate that had been translating into 60 to 100 bomber losses per month, even the lower bound of that range represented between 13 and 22 aircraft saved per month. Over the 4 months from December 1943 to April 1944, The lower bound of the range implied between 52 and 88 aircraft saved, between 520 and 880 American airmen who did not become casualties. These numbers were not published. The analysis was classified. The wire array's existence remained secret throughout the war. The German Luftwaffe Technical Intelligence Section became aware, by mid-1944, that American bombers were somehow producing reduced Liechtenstein radar returns. The night fighter crews were reporting shorter detection ranges against American aircraft in the period after the array's deployment. The German response was to begin developing a new radar operating at a different frequency, a development that the British Signals Intelligence Services monitored and that led to adjustments in the array's element length distribution that Sefton's team at Malvern implemented in a modified version of the installation kit in late 1944. The cat-and-mouse quality of this interaction, the German frequency shift, the Allied array modification, the potential German countermeasure, was exactly the kind of iterative technical competition that the electronic warfare community expected. What was unusual was that the Allied side of the competition had been initiated not by an electronic warfare laboratory, but by a maintenance sergeant with a spool of copper wire and 3 weeks of thinking time. Becker flew back to the United States in October of 1944. He had been in England for 2 years. The Army offered him reassignment to the Materiel Command as a technical consultant on the wire array program, which had by then been extended to B-24 Liberator bombers and was being evaluated for application to other aircraft types. He accepted the reassignment. He worked at Wright Field from November 1944 until his discharge in September 1945. During his time at Wright Field, he worked with the engineers who had reviewed his original specification and who had, in the 11 days of accelerated review that Pratt's cover letter had produced, developed a respect for the analysis behind the specification that did not fully survive contact with the bureaucratic reality of how the specification had arrived, from a maintenance sergeant without a formal engineering review, through a back channel created by a pilot's mission record and an electronic warfare officer's cover letter. Becker was patient with the engineers. He answered their questions. He explained the physics when they needed it explained. He deferred to their formal calculations when they produced numbers that differed from his by margins that mattered. He accepted 3 modifications to the installation design that the engineers' more rigorous analysis showed would improve performance, and he incorporated those modifications into the updated installation kit without friction. He was not interested in credit. He was interested in whether the thing worked. The thing worked. He had his answer. Everything else was maintenance. Albert Becker was discharged from the Army Air Forces in September of 1945. He returned to Evanston, Illinois, and resumed work as a licensed electrician. He spent the next 30 years wiring the buildings and industrial installations of the Chicago area with the same focused competence that had characterized his work before the war and his work during it. He did not speak publicly about the wire array for 20 years. The modification had been classified. When it was declassified in 1964, he received a letter from the Air Force Historical Division informing him of the change in classification status and inquiring whether he wished to make any public statement. He declined. He said in his reply that he had done his job and the modification had done its job, and he did not see what a public statement would add to either of those facts. A military historian named Colonel Thomas Morse found Becker in 1971 while researching electronic countermeasures in the European theater. Becker agreed to one interview, which lasted 3 hours and which produced the most detailed first-person account of the wire array's development that exists in the historical record. In the interview, Becker was precise and technical and patient with questions that required him to translate between the language of electrical engineering and the language of military history. He described the physics clearly. He described Morrison's dismissal without bitterness. He described Sefton with admiration. He described the installation program at the 91st Bomb Group with the matter-of-fact quality of a man describing work that had been done well and that was therefore complete. Morse asked him, near the end of the interview, what he thought about the statistical analysis showing between 520 and 880 airmen who might have survived because of the wire array. Becker said he thought about it carefully and regularly. He said that the number was an estimate with a wide range and that the true number might be lower or higher. He said that the men who survived because of the array did not know they had survived because of it, and that this was correct and appropriate, because what mattered was that they had survived, not that they knew the reason. He said that the wire cost about 40 cents per aircraft to install, that the copper came off spools that were already in every maintenance hangar in England, that the labor was 6 to 8 hours of maintenance technician time, that the material science was quarter wavelength dipoles at 490 megahertz, which was in any electrical engineering textbook. He said that the idea had been in the available knowledge for anyone who was listening carefully enough to the problem and broadly enough to the available solutions. He said that Morrison had been doing a job that required him to say no to things that hadn't been proven. He said that was a reasonable job for someone to do. He said he didn't hold it against him. Morse asked him if there was anything he wished had been different. Becker thought about this for a while. He said he wished someone had thought of it before Black Thursday, before August 17, 1943, before the 600 men. Then he said that wishing that was a waste of the time available, which was limited, and that the more useful activity was making sure that the next time someone in a maintenance hangar had an idea about a problem they were close enough to see clearly, the person they told it to listened longer than 10 minutes before calling it stupid. He said that was the lesson, not the physics, the listening. He went back to Evanston. He wired buildings for 9 more years before he retired. He died in 1987 at the age of 73. His obituary in the Evanston Review described him as a veteran electrician and World War II Army Air Forces veteran. It did not mention the wire. It did not mention the 490 megahertz. It did not mention the 900 B-17s or the reduced Liechtenstein detection range or the airmen whose names he never knew and whose survival he had contributed to from a maintenance hangar at Bassingbourn with a spool of copper wire and 3 weeks of careful thinking. The wire array's technical designation, AN/APQ-9 Radar Scatter Array, appears in one line of the Air Force's declassified countermeasures history, in a paragraph that describes it as a field-originated passive radar cross-section reduction system deployed across 8th Air Force B-17 units beginning February 1944. The paragraph attributes it to maintenance personnel of the 91st Bomb Group, without naming the maintenance personnel. His name was Albert Becker. He was an electrician from Evanston who had learned to listen to the systems he worked on, who had understood that the problem was the radar return from the aircraft rather than the signal the radar sent out, who had spent 3 weeks in a breast pocket verifying that the idea was right before he picked up the wire, who had been told the idea was stupid and filed the information carefully and continued thinking. The wire cost 40 cents per aircraft to install. The listening was free. And somewhere over Germany in the winter of 1943 and the spring of 1944, in the 1.6 kilometers between 4 kilometers of detection range and 2.4 kilometers of detection range, in the 900 meters of darkness that a German radar operator did not have time to resolve into a clean contact before the bomber flew past, the men who did not know why they were still alive went home. Some of them are still alive. They owe 40 cents of copper wire and a man who refused to stop thinking just because someone told him to.